So let's take a look at this problem. We have a bar A to B, and it's supported by two smooth collars. So first we find the bar A to B. Here's A, and then this must be the bar that goes between A and B, what I just colored red. And it's supported by two smooth collars. So this is a collar, we recognize that at B, and we recognize this collar at A. And what about the collars is they can slide along whatever they're coupled to, like a rod. They can slide along this rod from E to F, as well as this collar up here at B can slide along the rod that goes between C and D. Okay, let's continue to read the problem. At A, the connection is with the ball and socket joint. So we focus on A down here. We're going to cut through and do a free body diagram, so that ball and socket joint will be a very important feature. Let's continue to read. At B, at the other end, up here, it's a rigid collar, and so that's kind of shown by this part coming down attached to that collar. And so it's rigidly attached, but it still can slide along the smooth rod C to D. And a 95-pound load, here's our 95-pound load, is applied down here to the bar. Determine the reactions at A and B. And here are the answers for this problem. And probably I should have covered it up and forced you to go through it, but that would take a lot of time. So basically what it is we have, when we cut the member A to B free from the surroundings, we're going to have the load applied to it. Maybe I try and draw it like this, which will be part of the free body diagram, that load, as well as the reactions. And then we come in here and we say, well, what type of reactions do I have at A? Well, I have a reaction force at A, and the way we traditionally express it is as in Cartesian vector form, in components, AX, AY, and AZ. But it's really a force vector having three components in the I, J, K, AX, AY, and AZ. So for this one, with that ball and socket connected to a smooth collar, it'll have a non-zero, and I'll put it in the positive X direction, AX. Because the collar can slide, it will have a 0 AY. So that's just an observation that AY is 0 because it's a smooth collar. And it can have a non-zero AZ. Again, that's aligned with the Z-axis up here. So that's the way we would draw the supports for A to B. All right? Okay. We come up here. Well, first of all, with that ball and socket, can it have any moments at A? Any reacting moments? Well, because it's a ball and socket connected to that one, it can rotate smoothly. But when we get up to the other collar at B, you will have some non-zero moments. Okay, but let's focus on the forces at B first. So the forces at B, well, if I tried to pull it down, there would be a reaction force, a non-zero B sub Z pulling up. Okay, we would like to put in here a BX and a BY, but they're not independent, are they? And this is the crux of the matter. We look at that member C to D. It would have been nice if that member C to D would have been purely aligned with the x-axis. Maybe D, move it over, and be underneath this point back here. Then it would be only along the x-axis, and we would have a non-zero BX. We just have BY. Because it can slide along the rod that would be completely aligned with the x-axis. It's a smooth connection. But it's not. D is shifted over. So we have some component, a non-zero component in the x and a non-zero component in the y. And what we have to do is we really have to think about that for a while. It's very similar to a previous problem I solved earlier, but it was in 2D. It was a little easier to see. What we had is a rigid attachment, and we had this piece that came up like this, like that. And we had our collar, which could smoothly flow up and down on that rod, right? But our coordinate system was the traditional X and Y. And we talked about one non-zero force here with a given description of its orientation in 2D. There was a triangle that we were able to do, a 3, 4, 5 triangle, if my memory is correct. That's not the same as saying I have an independent Bx and an independent By. In that case, we don't. We just have a magnitude of the resultant force in a given direction. It's also like this. Sometimes we would say, what is my answer? You would say it would be F in the xi plus F in the yj in 2D. Or somebody could say it's the magnitude with a particular direction given. Sometimes answers are expressed just in Cartesian form, sometimes in a magnitude with the direction or orientation. Similar to this problem, magnitude with the given orientation by the similar triangle. Now in 3D, we have to step back. It's a little trickier to see. So let's go to the next slide, and maybe the next slide. There. And I think I gave this to you on the back of your handout. True? Okay. So what I tried to do was take and have a perspective of looking straight down from positive z, looking straight down. All right. And I had to shift it a little bit because I wanted x to be straight north, so to speak, or up. And then that's the positive x direction. And the positive y direction is this way and here. So it's going to take a while to orient. I'm looking down, so I have a 2D projection. All right, and then I said, well, where is my point C in that projection? Well, it's right on the z-axis, which is right at the origin, which is the xy. So I put the point C in there, and I labeled where it's at. It's at 0, 0. 0 in the x and 0 in the y. All right, then we said, well, where is this point D? And we look at it, and after a little bit of discerning, it's 3 foot in the positive y, and it's 9 foot in the negative x. So in the negative x, mark off down here to negative 9, and then in the y, mark off positive 3, and there's its location. Hopefully this is not too confusing, but it's nice to have a projection, so in 2D it's a little easier to see. And then what we can do is we can say that rod from C to D lives in this plane. They have the same elevation. I mean, they could have made this problem really tricky, and they would have had it sloping in the Z. Wow, that would have been more difficult. But it's the same. It's in a plane of constant Z. So I can get a description of that, and I put from D to C, so it goes this way. And so the displacement vector from D to C is 9. And I should have put my units of foot, right? 9 foot I minus 3 foot J. Is that right? Yeah. So from D to C. Sometimes I work from C to D, or Michelle and I were working from C to D, but this is, I've switched it around, go from D to C. All right. So you're going to move up 9 in the X and back 3 in the Y. Get a unit vector. You've done that a lot. So that gives me the direction from D to C. My force that collar cannot support anything from sliding back and forth, but it's going to generate something that's perpendicular to that line C to D or D to C. So I'm really interested in getting this perpendicular unit vector. Well, we did it for that similar triangle when I rotated at 90 degrees. So if you have a similar triangle, I don't know, draw it like this. Here's a 3, 4, 5. So I'm going to bring this up. So that'll be 3. Then this will be 4. And that's a bad looking triangle. Draw it to scale. Try to draw it to scale. There's 5, 3. There you go. Okay. Well, here what you do is you're thinking, okay, if I rotate it 90 degrees, this vector is going to be going out a lot in the y, in the positive y, and it's also going to be moving in the positive, here, like this. It'll be moving quite a bit in the positive y as well as the positive x. You just look at it and you say, oh, it's going to move out now 9 in the y and up 3 in the x, and that's the direction. So positive not 3 plus positive 9 in the I and j. And then we normalize it by square root of 90, which is 3 squared plus 9 squared. So here is my unit vector. What is that normal to? The rod that they can slide along. And so my reaction force, the two components of it, have to live, in that direction. So when we come back here, we're going to say, I'm going to have, we already did these two parts. This b sub n is a magnitude of a vector times a unit vector giving me the direction, that normal direction. So I don't have two independent forces, reaction forces at B in the X and the Y. I have only one magnitude and their orientation is linked. If you get over that hump, I think it's going to be downhill. It'll still be a lot of work, but it'll be downhill. So what do we have is we have this. Also, we can have moments. That's the other reaction. So it's easy to understand if I take that rod and I try and twist it back and forth around the z-axis, it can generate a non-zero mb in the z-axis. So that would be the non-zero reaction moment at B in the z. Likewise, I can't twist it. I can. It'll resist a moment in the same direction that the force. All right. And so you get a non-zero moment at the point B in that normal direction. Remember, the moment is a vector, just like a force is a vector. Use your right-hand rule, put your thumb in the positive direction of that vector, and it's curling the way your right-hand fingers would curl. Okay, so there is my good free body diagram. What do I have? Two possible non-zero moment reactions. Both of them are at B. Why do I even separate it? You could even just say, well, we have a non-zero moment reaction at B, but it's going to be the I and the J are related, and the K is really independent of the two. So this would be MBZ, this part, and then here I would basically put those two together and I'd multiply by the magnitude MBN times the U normal in the X and the U normal in the Y. What is the U normal in the X? About 31%, 30.316228, blah, 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 if you want it numerically. Or it's 3 divided by the square root of 9, 90. Likewise, that magnitude in the J is given right there. Okay. So at this point, what we can do is we can now write our equations and solve for them. Now, some of these problems are very hard because you have 1, 2, 3, 4, 5, 6 unknowns. You see the unknowns? We just counted them. And at most, you're going to have 6 equations. 6 unknowns, 6 equations. I hope they're not too tightly coupled such that I have to solve them all at the same time. Sometimes we can get one equation that has only one unknown, and then it's like goes pretty fast. Usually, to solve these a little faster, it would be the moment equations, which often can give you one equation with one unknown. After you solve a few problems, you will start to see that pattern. Oh, maybe I'll try the sum of the moments, especially in 2D. Our equilibrium equations are really the sum of the moments about a particular point equal to 0, and then the sum of the forces any place on the object equal to 0. Both of these are vector equations, and then what we do is we treat them as 3 scalar equations and 3 scalar equations. The sum of the forces x, y, and z are pretty easy. The moment equation really is the sum of the moments about some x-axis that goes through the point of interest. the sum of the moments of the y-axis through the point of interest, and the sum of the moments about the z-axis going through that point of interest. That's a long description of what we're really doing. So your point of interest could be point A. That's a logical point of interest. It'll work. Your point of interest could be this unlabeled point where the 95-pound force goes through my rod. Your point of interest could be the origin, point E, as labeled here. Your point of interest could be point B. Your point of interest could be D. This, you see, we're starting to get more and more options. It's not obvious where our point of interest is. And there will give you, if you do the math right, all of them will work. Just some will be a little more complex. So we were working together and Michelle said, let's pick B. Okay, let's pick B. Point B. Why did she pick B? Well, because it knocks out probably this B sub n. Okay? And that's probably the most complicated one. And you want to treat these scalars. So let's do this one. If I'm going to have the x-axis going through the point of B, I'm going to have the y-axis going through the point of B, and the z-axis going through the point of B. You want to try the x-axis? So sum of the moments around the x-axis that go through point B. That equals to 0. Okay, what's the equation look like? Does AX induce a moment about the x-axis? You have to kind of go through the whole thing. No, it doesn't. How about AZ? Does that induce a moment? Well, this x-axis goes right on top of. If you go straight up from A, you don't hit this smooth rod, you hit the axis X, don't you? So it doesn't induce a moment about the x-axis going through point B. Now, look, if I would have said, let's do it around this point, guess what? It does induce a moment around the x-axis going through point C, but that's not what we picked. We picked point B. And B, I drop straight down and then straight over. And so if I come straight up, I will go right through that axis. So a little discussion there. It takes a while to see it, but this does not induce a moment. How about the 95 pounds? Does it induce a moment about the x-axis? Yeah, okay. And its moment arm distance is 6 foot. And tell me, this is the positive direction for the x-axis. Is it going to make it want to rotate in the positive direction using your right-hand rule, or the negative direction? Positive. Very good. So it'll be the 95-pound force times its moment arm distance of 6 foot in the positive direction around the x-axis going through point B. Okay. How about the normal force B sub n going through point B? No. How about B sub z? No, they both go through point B. That's nice. How about the moment MBZ? Does that induce a moment about the x-axis? I'm going through each of our 6 unknowns. Does this one right here induce a moment? No, it's purely around the z-axis, isn't it? I mean, that's what it is. It's a moment at point B around the z-axis. All right, it's like asking somebody, John, yeah, that's your name, John. Okay, is your name Fred? No, your name is not Fred. Your name is John. So it's almost too obvious. Okay. All right, now, how about this one? MBX. Does it induce a moment about the x-axis? It does. And our equation was just like this. For maybe I should have wrote that out. We'll have B sub n is equal to the magnitude of B sub n times that unit vector. I forgot the magnitude. It was sometimes it's better to work with the magnitudes. What is my magnitude of that unit vector? 0.31622 whatever 8 I, and then plus 0.94868 j 0k. I ran out of room. And then likewise we have the moment B right here in the normal direction. Okay, and so it has a magnitude of that B in the normal direction times that same unit vector, 0.3162I plus 0.94868J plus 0K. So yeah, and so basically what we pick up is we pick up the 0.3162 times MBN. Do I have a moment arm distance like we had a moment arm distance for the 95-pound force? Do I need a moment arm distance? No, it's already a moment. It's already a moment. And so that's equal to 0. Guess what we can solve for? One equation, one unknown. You could solve for the magnitude of B sub n. And when we solve for the magnitude of B sub n, that comes in at negative 1802.5. What are the units on that? Foot-pounds? Right? It's a moment. All right. All right. Let's do the next one. Let's do the sum of the moments about the y-axis that goes through point B. I know the book doesn't use these long subscripts, but I like to clarify. What exactly are we doing? And, okay. So about the y-axis, where's our y-axis? It's aligned like this. Right? B sub n is not aligned with the y-axis. We already talked about that. It's living in that xy plane, but it's not aligned. Okay, this force is aligned with the y-axis. Okay, so we go, does AX induce a moment about the y-axis that goes through the point B? Remember, it's going through the point B. It does, doesn't it? Doesn't AX induce a moment about the y-axis going through point B? And isn't its moment arm distance 6 foot? It's 6 foot below it. Point B is 6 foot above point A. Okay, and so basically we're going to have the magnitude AX times a moment arm distance 6 foot. All right. And then I use my right-hand rule, putting my thumb in the positive y-axis direction at point B, and I'm thinking, does that make it want to rotate in a positive or negative sense? Negative. Okay, I feel like I should slow down, but I don't want to slow down. I'll run out of time. Did you follow that? Okay. How about now, AZ? Does that induce a moment about the y-axis going through point B? Yes, it does. Okay, so we'll put AZ, the magnitude. What is its perpendicular moment arm distance? 5 foot. That's very good, 5 foot. And now we use our right-hand rule to determine, is it a positive sense or a negative sense of rotation? Negative sense. Excellent. Thank you. You're following along. Good. All right. The 95, did we already talk about that? Does the 95-pound force load induce a moment? No, because it's completely aligned in the y-axis. Okay. Then we come up here, and we have, how about this MBN? Hey, we did that already. We're going to have MBN times that component, which is in the y-axis, which is 0.948... 948,683, whatever that number was. Okay. How about the force, BN? Does it induce? No. How about the force, I'm getting this all cluttered up here. I have to erase some of this, sorry. How about the force BZ? Does it induce a moment? No. That's why we picked B. All right. So there it is. That's the end of it. And we do know this one. We solved for it already, but we have an equation with two unknowns. So we just keep going on, and when we can solve for one of those unknowns, we'll come back. What, right? All right. Let's try this. Let's try the sum of the forces in the y direction. They equal to 0. Let's try that equation. If you try that equation, neither AX or AY, that's obvious, have a component in the Y. But we do have the 95-pound force. It's pulling in the Y. And then we look back here, and neither the moments or this BZ have a component of force in the Y, but BN does. right? And won't that be Bn times that part in the y is 0.94868, blah, blah, blah. That Bn times that, and that's equal to 0. At this point, that's positive, and can we solve for Bn? Yeah. And then when you solve for Bn, the magnitude of Bn, we come in at negative 100.14 pounds. So maybe I box that, just like maybe I should have boxed this. Actually, we solved for two of the hardest parts right away. Okay, let's do this. Let's do the sum of the forces in the x direction. What does that give us? Well, we're going to have AX there. Nothing there. Come up here. We'll have plus Bn times u in the x. U in the x was 0.3162228. Okay. And the moments don't, and BZ doesn't, so that's now only two players. And we can now solve for AX. And AX comes in at 31.67 pounds. What you're doing is you're getting two vector equations or six scalar equations and looking to solve for the six unknowns. And your strategy of which one to try first is probably a little different than your fellow, co-workers' strategy. But we got 1, 2, 3 of those unknowns. Okay. Should we continue on, or do you have the gist of it? Do you have the gist of it? Can you finish this one out? I mean, at this point, we just solved for AX, right? Because we just solved for AX, guess what I can do? Come up here, I can plug it into that equation, and I solve for AZ, right? And then I'm looking, and I used the force equation, moment around this axis, moment about that axis. I have one more moment axis equation, and one more direction of the forces. So I'll finish it out. But so AX comes in from that equation. Hold it. AX is what we solve for. So we're solving from this equation for AZ, right? And AZ comes in at negative 380 pounds from that equation. And you should check it. I encourage you to check it. And then let's do the sum of the forces in the Z. Okay, if we do the sum of the forces in the Z, all we get is that AZ plus BZ is equal to 0. We just solve for AZ, so we find that BZ is negative of negative 380, so it's positive 380 pounds. And then the last one is the sum of the moments around the Z-axis. When we do the sum of the moments around the Z-axis that goes through point B, that must equal to 0. What we find is that we solve for the moment, and I'm trying to think about this for a minute. The AZ, BZ, well, it's going to give you an equation, and you get that the moment at point B, the reaction moment around the Z-axis is 0. I run out of room, so I'm going to say that these, you can go back and you can express. What is this? This is FAX. What is this? FAY. We said it was 0. We didn't even put it in there, did we? The AY. And then this is the FAZ or AZ, which we found to be negative. How about the vector representation of the reaction force at B? Well, you basically have these two components come from the B sub n times U in the X for that one, and this is b sub n times u in the y for that one. And then that one was our bz. And then for these three components, that is the moment b sub n times u sub x, and this is the moment b sub n times u sub y. Any comments or questions? I need to move on if that's okay. All right, let's move on.